Hello and welcome back. Today we're going to speak about number systems. We're going to cover decimal, binary, octal, and hexadecimal systems. In the decimal system, it's called base 10. We have those digits from 0 to 9 that we are using. So now when you have 8,327 base 10, this means 8,000 plus 300 plus 20 plus 7, which using the powers of 10, it's 8 times 10 to the power 3 plus 3 times 10 to the power 2, 1, 0. Now, in binary system, base 2, you can only use 0 and 1. So now if you have this number in base 2, binary number, what does this really mean in decimal number? This means that you multiply these digits by the powers of 2. So started from here to the power 0, 1, 2, 3, 4, 5, 6. When you do the math, you get 64 for this one here, 8 for this one here, 4 and 1, and you get 77 base 10. Now, octal system, that's base 8. These are the digits that are allowed to use, 0, 1, 2, 3, 4, 5, 6, 7. So now if you have a number here in base 8, don't read it 7,403. No, that's only when you have a base 10 decimal numbers. This one here, you can say 7403 base 8. And you see how we multiply this 3 by 8 to the power 0, 0 times 8 to the power 1, 4 times 8 to the power 2, 7 times 8 to the power 3. You do the math and you get these numbers, you add them up and you get 3,843 in base 10. Now hexadecimal system, that's base 16. This is the digits that you can use, 0, 1, 2, 3, 4 up to 9, and then A, B, C, D, E, F. A is for 10, B for 11, C 12, D 13, E 14, F 15. So now when you have a number like this in base 16, obviously that's base 16. You can see that because of E and A here. So now how do you do that? Turn it into a base 10 decimal number. You multiply by the powers of 16 to the power 0, to the power 1, to the power 2, to the power 3. You do the math and you get 32,419 in base 10. Now these are, this is a table of the powers of the bases. So for base 2, you have 1, 2, 4, 8, 16. Base 8, you have 1, 8, 64, 5, 12. Base 10, you have 1, 10, 100, 1,000, 10,000, and so on and so forth. Now, this table gives you the starting numbers. In base 10, 0, 1, 2, you get to 9, and there you run out of digits, then becomes 10, 11, 12, 13. We have names for those, 20, 21, etc. In base 2, you have 0, 1, and then 1, 0 is for 2, 1, 1 for 3, and then 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and you keep going. For 16 is 1, 0, 0, 0, 0. Base 8 starts from 0 up to 7. Now you run out of digits, then this will be 8. Don't read it 10. No, it's 1, 0. Base 8. 1, 1, 1, 12, 1, 2, 1, 0. Base 16, 0 up to 9 and A, B, C, D, E, F. Now done. 16, B, 1, 0, 1, 1, 1, 2, and so on. You continue that way. Now we're going to see how to convert a decimal number to a binary number. Convert the decimal number 235 to binary number. So now we do divisions, sequence of divisions by 2. So when you divide 235 by 2, you get 117, and the remainder is 1. You continue. 117 divided by 2 is 58, and the remainder is 1. 58 divided by 2 is 29, and the remainder is 0. 29 divided by 2, 14, and the remainder is 1. Divided by 2, 7, and the remainder is 0. Divided by 2 is 3, the remainder is 1. Divided by 2 is 1, and the remainder is 1. Divided by 2 is 0, and the remainder is 1. So once you have that, then you make sure you look at these numbers this way, and you start dropping it this way. That will be your answer. So 235 base 10 is 1110111 in base 2. So now I want you to pause the recording, take a minute, and see if you can convert this decimal number 77 into a binary number. Okay, let's see if you got the answer. It should be 1001101 in base 2. Now converting decimal to octal the same way, but now we divide by 8. So we divide 3,843 by 8. You get 480, and the remainder is 3. Remember, the remainders here will be from 0 to 7. Those are your remainders. It could be one of these numbers. This is divided by 8. You get 60, and the remainder is 0. 60 divided by 8, you get 7, and the remainder is 4. 7 divided by 8 is 0, and the remainder is 7. So now we do the same thing. We take these numbers and drop it this way, and we get this answer. So 3,843 base 10 is 7403 in base 8 as an octal number. Now it's your turn. Pause and solve. We need to convert this number 8759 to octal number. If you did it all right, you get this answer here. Now we are going to do converting decimal to hexadecimal, base 16. This is a decimal number here. I want to convert it to an hexadecimal. Remember, we start dividing by 16, and the remainder will be any number between 0, 9, or A, B, C, D, E, and F. So when you divide this by this, you get 26, and the remainder is 3. You divide by 16, 126, and the remainder is 10, which is A. Divide by 10 by 16 is 7, and the remainder is 14, which is E. 7 divided by 16 is 0, and the remainder is 7. Now remember, always at the end you get a 0 here, but you don't put it right here. We don't need it anymore. So now we do the same way. We go like that, and we get our answer is 7EA3 base 16. Okay, now you convert this decimal number 3978 into an hexadecimal number. Okay, let's see if you got it right. This will be the answer is F8A base 16. Very good. Now we are going to do conversion between base 2 and base 8. So I have this number here. I want to convert it to an octal number. Now, one might think, why don't I take this, turn it into a decimal number by multiplying by the powers of 2? It's a nightmare. And then after I get a decimal number, I start dividing by 8 to turn it into an octal number. That is a long, unnecessary way of doing it, and most likely you will get it wrong. Instead, here's what we will do with this thing to turn it to a base 8. So we take this number and we divide it from right to left into group of 3. Group of 3. Now, you need this table here. That's the conversion table between base 8 and base 2. And remember here, I have to have 3 digits here. So you complete the pattern, okay? It's 3 digits here. So now you get here, 0, 1, 0. 0, 1, 0 is 2. 110, 110 is 6, 111 is 7, 100 is 4, 010 is 2, and that's your answer in base 2. Very straightforward, easy. Group them, group of 3 from right to left. Therefore, this number, this long binary number, is this in base 8. Now it's your turn. Convert this octal number, that's an octal number now, to a binary number. Okay, let's see if you got it right. This is your octal number. You you look at these digits and see what do they correspond to in base 2. Remember, you have to have 3 here, okay? So 6 will be 110, 4 will be 100, 2 will be 010, 7 will be 111, 5 will be 101, 3 will be 011, and that's the answer now. It's very straightforward. Okay. Now, conversion between base 2 and base 16, the same concept, but now you need to divide the number into groups of 4 because you need 4 digits to correspond between the base 16 and base 2. Okay. So we could take this number here and start dividing it group of 4 from right to left. See how I completed the pattern here? Now I look at 0010, 0010, 0010 is 2, and 1111 is F. 1001, 1001 is 9, and 0010 is 2, and therefore here is the answer, converting base 2 to base 16. Now it's your turn, pause and solve. This number is in base 16 and I need to turn it into base 2. See if you can do it. Okay, let's see what you did. So that's base 16. Base 16, now I need to go from here, see the correspondence in base 2. So 2 is 010, 0110, and then A is 1010, 7, C, 3, and here is your conversion, base 16 to base 2. Now, how do you convert between base 8 and base 16? It's really now simple. If you have a number in base 8, you want to take it to base 16. Base 8, turn it first into base 2. Remember, groups of 3. Then you regroup it, groups in 4 to go to base 16. If you have a number in base 16 and you want to turn it to base 8, base 16, cut the number into base 16, represented as a groups of 4 into base 2. Now from base 2, you redivide that groups of 3 to go to base 8. Let's see how that's done. Here's a number, base 8, I need to turn it into hexadecimal number. So I need the two tables. Base 8 is this. So 7 is 110. Now I'm going to 8 to 2 now. 8 to 2. 8 to 2. So 7 is 111. 5 is 101. 4 is 100. 6 is 110. 7 is 111. So I turn this octal number into this binary number and start now dividing it from right to left, group of 4. Okay, and then I put a 0 here. And now 1111 is F. And then 0010 is 2, 1101 is D, 0111 is 7, and we got the answer. So again, this base 8 is this base 16. Now it's your turn to convert this number, base 16, to an octal number. Okay, let's see how we do that. This is base 16. You take A is 1010, 4 0100, C 1100, F 1111, 8 1000. Now you divide them because that was divided group by 4, right? And now you take this number again, divided group of 3. You have this, 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 and then you go 2, 1, 1, 6, 7, 1, 2. Now let's learn about adding two binary numbers. This is the table. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 actually in decimal number is 2. 2 is 1, 0. So 0 and you carry 1. So let's do that. So you say 1 plus 1 is 0 and you carry 1. Now 1 plus 1 again is 0, you carry 1. 1 plus 1 is 0, you carry 1 plus 1 is 1 and you carry 1. 1 plus 1 is 0. Okay, so let's see how it's done. 0, you carry 1, 0, you carry 1, 1, you carry 1, 0, 1. All right, try it yourself. Now add these two binary numbers, pause and solve. Okay, so you see like 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0, you carry 1, 1 plus 1 plus 1 is 1, you carry 1, 1 plus 1 is 0, 1. Now, adding two octal numbers. Now, this is the table, but I will show you, you really don't need to memorize this table. I will show you how you can do it. But what is this table does? 3 plus 3 is 6. Fine, I'm still within the base. 3 plus 5 is 8. 8 is 1, 0. 9 is 1, 1. 1, 2, 1, 3, 1, 4, and so on and so forth. Now, I will show you how to do the addition without having to look at this table. So we're going to add these two numbers. I look at it this way. What is 3 plus 6? 3 plus 6 is 9. I am in base 8. 9 means 1 and you carry 1. 9 is 1 plus 8. Now 1 plus 5 is 6. Plus 7 is 13. 13 is 5 plus 8. 1 plus 7 is 8, plus 2 is 10. 10 is 2. So again, look at this, 5 plus 7, 5 plus 7. Oh, there's something, some 12. No, I didn't, oh, because no, I have 1 here. 1 plus 5 is 6. 6 plus 7 is 13. 6 plus 7, see, is 5, and you carry 1. Okay? So, okay, so that's good. So you really don't need the table. You can read it directly. Now it's your turn. Add these two octal numbers. Let's see if you got it right. You get this 5273 base 8. Now, adding two hexadecimal numbers, no need for a table. Remember, A is 10, B is 11, C is 12, D is 13, 14, 15 for E and F. Okay, we're going to add these two numbers. Let me show you how you don't need any table. You are in base 16, remember that. So 8 plus 6 is 14, and 14 is E. Here's E. 7 plus B, what is B? B 11. 11 and 7 is 18. 18 is 2 plus 16. 2 plus 16. Carry 1. 1 plus A is 10, 11. And C is 12, that's 23. 23 is 7 plus 16. 1 plus 4, 5. 5 plus 7 is 12. 12 is 12. 12 is C. Okay, it's very straightforward. Now it's your turn. Add these two hexadecimal numbers. Let's see if you got it right. Okay. Now we're going to talk about how to represent binary numbers in the computer representations. Now we're going to talk about here an 8-bit machine, 4-bit machine. You can have 16-bit machine, 32-bit machine, 64-bit machine, bigger machines. So this here is the sign bit, meaning the computer decides whether your number is negative or positive by looking at this bit. If it's 0, the number is positive. If it's 1, the number is negative. And now remember is in 8-bit machine, you can handle numbers between -128 to 127. Anything beyond that, the machine is incapable of dealing with. Then what do? You just use a bigger machine. The same thing here. So now, how to represent 25 in an 8-bit machine? Remember 8, so my pattern is 8. So first of all, you convert 25 into binary number. When you convert 25 into binary number, you get 1, 1, 0, 0, 1. Now, don't leave it like that because you need 8-bit machine. So you have to complete this like that. 1, 2, 3, 4, 5, 6, 7. You have now 8 digits here, and it's positive. We know that, and will be represented by this number. Notice we use the 8 bits, very important. Now, how to represent a negative number, -25? So first, 3 steps. Step 1, represent 25. Ignore the sign. And we did it earlier. That's 25. Now, take the complement. This is an E, I think. Take the complement, which means replace 0 by 1 and 1 by 0. 0 by 1 and 1 by 0, which you get this number. Now, add 1. You add 1 here. And you get this number, which represents -25. Example, what does this number x 10100111 in 8-bit machine represent? So this number here is a negative number. Why? Because of this one here. So I know it's a negative number. So if I can find its absolute value, then I know what the number is. So take the 2 complement, replacing 1s by 0s. Add 1, you get this. And this one here in base 2 is 89. Therefore, my number is -89. In 8-bit machines, here are the representations of the negatives and positive numbers. And that's really easy. I mean, you can find any one of these by using the same methods here. You look at how we got this here, for instance. 4 is 0, 1, 0, 0. The 2 complement 1, 0, 1, 1. Add 1. 1 plus 1 is 0. 1 plus 1 is 0. 1, 1, and that's 1, 1, 0, 0. That's how you do all of these here, okay? So this is a table. Now, adding decimal numbers in 4-bit machine. This is just an example, okay? So if you want to add 5 plus -7, put the 5, put the -7, add them, and you get -2. If you want to add 2 plus 3, 2 is there, 3 is there, add them, you get 5. If you add 3 plus 7, 3, 7, you get this, which is -6, which is completely wrong. Completely wrong. Why this happened? Because you're adding 2 numbers, their total exceeding the capacity of the machine. The machine can handle up to 7 only. You have 10 here. 3 plus 7 is 10. So the machine cannot handle this addition. So what do you do in this case? You just use a bigger machine. So now, instead of giving you a negative number which is wrong, nobody would buy a calculator like that. It will issue an overflow message for you that's exceeding the machine's capacity or whatever. Now, can you add the decimal 70 plus 85 in an 8-bit machine? I think. The answer is no, because 70 plus 85 is 155, which exceeds the capacity of the machine, which can handle numbers between 126 minus and 127. Therefore, the answer is no. The machine cannot handle this addition. Then what do? You use 16-bit machine, 32-bit machine. There's a limit at the end. That's when we use scientific notation, and that's completely different than what I'm doing here. Here's the last example, is if you're adding, by the way, go back here. If you're adding in any of these systems a negative and a positive number, it will work for you. The problem is when you're adding two negative numbers and you get less than 128, or when you are adding two positive numbers and you're exceeding the 127, that will be a problem. So now we're going to add 7 plus minus 5, that's going to work. 7 minus 5. When you add these two numbers, you find out like there's a 1 here that comes after this. And this is not really an error. This one will be this lost, truncated, we call it, truncated, and the answer 2 is correct. And that is the end of number systems. I hope you enjoyed it. Please subscribe, and I will see you soon. Thank you.